soccer game on ground. We have Michael Ferrer, our FPGA engineer, Matthew Cabral, our hardware engineer, and Sanjay Chan, our software engineer. Our project involved making a side-scan sonar system, and it's basically a system that uses transducers to transmit and receive high-frequency signals to acoustically map out a seabed, similar to a medical ultrasound device. Our objective was to create the electronics that create high-frequency variable signal, sending it out, read it back in, and then process and store those samples to an SD card. We needed to use a field programmable gate array, or FPGA, in order to deal with the high-frequency speeds, and we needed an external ECE, or analog digital converter, in order to get the higher quality resolution we wanted for their image. If the project was a success, then we would be able to deliver our system to the customer. We would connect their transducers to it, and then they can go on a test run, and then take that data, put it into imaging software, and then see a map of where they've been.
So we came up with 6 custom requirements for our project with our sponsor. The first was creating a broadband signal at about 1.1 megahertz. The next was implementing a 4-channel ADC. After that, it was storing memory to an SD card. Implementing a timestamp, image processing, and determining the rate of pulses. The engineering requirements were basically the customer requirements broken down a little further. They included some more information for the requirements as well as a test method for each. To start off with just generating a broadband signal across different frequencies. Implementing the ADC was split into 2.1, implement the analog to digital conversion, and then 2.2, programming the ADC. Memory was also split into 2 different subsections, being able to store samples and then developing a method to process that signal. 4.1 was timestamps for our data. 5.1 was being able to process an image received of the signal. And then 6.1 was determining a rate of pulses. We also came up with constraints and standards for the project with our sponsor. Our constraints were pretty much goals that we wanted to meet for the project, such as having 4 channels for our final design, implementing 16 bits or having a greater dynamic range for the project, and being able to sample at 2.5 megasamples per second. Our standards were a way for us to stay consistent throughout our project in regards to equipment used and programs. Some of these included USB 2.0, SPI and LVDS communication, and VHDL and C programming. Here's a diagram of our high-level design for our project. It starts off by entering data into the human-machine interface. A signal is then generated through the PWM of the FPGA. The side-scan sonar transducers then take the echo of that signal, which is then filtered and converted through the ADC into a digital signal. That signal is then processed back through the FPGA, and the signal is then saved onto an SD card. The data from that SD card is then uploaded to a computer for image processing.
For the alternatives, there were 2 different sections, which includes the FPGA and the ADC. According to the aforementioned standards and constraints, the chosen FPGA required a low pin count FMC connector to interface with external ADCs. The Z board was the perfect fit as it met the criteria. For the ADC, the chosen ADC that we picked was the AFE 5812 evaluation module because it exceeded the requirements and can connect to the Z board via the adapter board. Also, the resolution can increase and the sample rate can decrease due to decimation and demodulation. Decimation is basically having the extracting the information from the transmitted signals, and demodulation is reducing the sample rate so that the complexity of the system is not too complex. For the technical design, consists of the test setup, the software, and the hardware. So the test setup allowed the ADC inputs and FPGA generate signals to be viewed through an oscilloscope and monitor the transmit and receive modes via the LEDs. For the FPGA setup, this setup allows us to see a change in frequency and then view the frequency, monitor on the oscilloscope depending on the combination and position of switches. The input signal to the ADC sent through the function generator can be monitored on the oscilloscope given the correct PMOD port being probed. Lastly, our design allowed the ADC GUI to confirm that the ADC was correctly communicating with the FPGA by setting test patterns and monitoring it with the oscilloscope. So for the software setup, it involves, it's basically a summary of the software design that was coded in the Silence SDK. So when the software runs, a square wave signal is generated via the ADC, via the FPGA, and the signal is received by the ADCs so that it can be processed and stored in a memory.
We have a couple of test cases here. The first one is the variable frequency signal. We need to be able to create a signal that can be generated up to about 1.1 megahertz. The next one was to communicate from the FPGA to the ADC efficiently. So we need to be able to make sure that we can send a signal into the ADC and be able to read it on the FPGA. The next one was to program the ADC using the ADC's GUI and make sure it was correctly programming the ADC. And then the last one would be memory, which we want to be able to store sample data in the FPGA onto an SD card. For the variable frequency signal, we were able to generate a signal from around 200 kilohertz to around 50 megahertz, so that, and output it to a PMOD port, which was seen on an oscilloscope. So that was successful, and it encompasses the transmit section of our design. Then we tested the communication to the FPGA, where we inputted a signal using a function generator to the ADC and mapped that to a output port on the FPGA. The output port on the FPGA is then monitored with using an oscilloscope, so we can see that the correct frequency is being transferred to the FPGA and the communication is correct. Then the programming the ADC, we are able to monitor the serial communication with a logic analyzer on the ADC and confirm that what we are programming on the GUI of the ADC is actually what's being programmed on the ADC. The memory portion, we were unable to test because we did not build the memory circuit within the FPGA design, and the research was done into how to do it. We just did not end up having enough time to get to it. The test result for the transmit, you can see the 450 kilohertz signal being generated. If we were to, there's 8 onboard switches of the FPGA, and if these switches are changed in different combinations, you're able to change the frequency, giving it variability. And this would be the received, where you can see the function generator sending out a 450 kilohertz signal. and it being seen on the oscilloscope through the output of an FPGA board.
So this was the schedule that we created at the beginning of the semester. We took all the tasks that we knew we needed to complete, and assigned a team member to each one to make sure that there was some responsibility on the project. We first started by making a weekly schedule that showed all our available hours outside of classes during the week, and assigned those as our planned hours for each task. Those can be seen highlighted in green, and what we actually found when we went to work on is that, well, one, we didn't have enough time because all our classwork that we had to do when studying, and two, that we severely underestimated our tasks. We fell behind in most of the beginning ones because we had to learn FPGA design from scratch, and none of us are computer engineers, we're all electrical, so we're learning from tutorials and sources online. The actual hours that we worked are underneath the planned hours. The highlighted in the blue section shows when we're working on it while on schedule, and the orange highlight shows that we're working on that task after we plan to have finished it. Only after we completed a tutorial and gained a basic understanding of how to design FPGAs were we able to start completing tasks such as the PW output, or this is a square wave output, communication between the two. Overall, we worked about half the hours that we planned, which still wasn't as much. We planned 19 hours for the output, and we actually put 105. So it was both a combination of not having enough time and underestimating how long it would take. Overall, we were able to create two modes that worked on a loop-based system. In the receive mode, we can take signals from the ADC using LVDS, or low voltage differential signal and communication. And we're able to read that in from the FPGA and put it onto a PMOD port where we can see it. We're also able to see the ADC clock on it, and we can use the GUI to send test patterns to verify that yes, we are communicating properly and reading it as is. We have the transmit mode, and with that we can create a square wave signal, and we can use the switches to select whichever frequency we want, ranging from about 200 kilohertz to 50 megahertz. And we use the onboard LEDs to show which mode that we're in, as well as showing that we have actually pushed the code towards the mode. Throughout this process, we've learned the engineering design process and how it's iterative and it's always repeating and building upon itself, as well as learning to research board configurations, trying to find the optimal design, balancing benefits, features, and then costs. We learned how to schedule tasks and plan them out based on skill set and interests, and time management as well, making sure that you're not wasting time with what you're doing. When you're putting time in, you're actually making progress. We learned to develop test procedures to confirm that every system that we've created is working as we believe. And finally, FPGA design and implementation, where we all have a software-based mindset, doing things in loops, polling, or interrupt-based, and actually switching away from software to hardware to perform simple tasks really well without bogging down the software. And now we have a demo. All right, so right now we're in receive mode, and can you do a test pattern real quick? So in the GUI, we're able to do a test pattern, and if you went to all ones, we would see that that blue line goes all the way up high, and if you go to all zeros, low, and then toggle, and then you can see it toggling fast rate. If you put back to none, you can see that we have noise here that's actually the 14-bit representation of the voltage that the ADC is reading right now. And we have a function generator, and it's at 450 kilohertz sine wave, and if we hit run, and we go over here, we can actually kind of see that it does have instruments. There it is, 418 kilohertz, and that's with me playing around with it. If I just let it run, and then I disable it, now it's just noise. But here you can actually see that the 450 kilohertz is impacting that signal. All right. Yeah, so now we're going to go to the transmit mode. Hold on. I just need to change that one. There we go. Like that. And once we push it, we'll actually see a couple of LEDs lit up on the board, so that way we know, yes, the code has been pushed through. All right, so now we're no longer in receive mode, that has been disabled, and we're in transmit mode. If I just pause it right here, I can measure that. So right now it's measuring 533 kilohertz, and if we adjust our switches, there. So now we're at a different frequency. I think we're at 900 kilohertz, and then keeps high. Yep, 943 kilohertz I saw, and right here is our 450 kilohertz signal. And these two, 450 kilohertz and 900 kilohertz, are the resonant frequencies of the transducers that we find in interface. And any questions?